we're going to have a quick look at how we do calculations involving gases. So what we've looked at previously is calculating the moles of a gas at room temperature and pressure. So if you've got a gas at room temperature and pressure, 1 mole of that gas will occupy 24 decimeters cubed. So the equation that we used was this one here. So volume equals 24 times the moles. In terms of the units for everything, volume should be in decimeters cubed, especially if using 24, because 24 is the molar gas volume, and that is done in decimeters cubed per mole, like so. Okay, so if your gas is at room temperature and pressure, that means you can use this equation here. If you don't have it at room temperature and pressure, that's when the ideal gas equation comes into play. So when using the ideal gas equation, there are a couple of assumptions that you make to basically classify that gas as an ideal gas. Okay, so when it comes to an ideal gas, the assumptions that we make is that that there are no intermolecular forces between the gas molecules. Okay, so by intermolecular forces, that's talking about hydrogen bonds, London forces, permanent dipole-dipole interactions like that. So we assume that between the gas molecules there are no intermolecular forces attracting them. We also assume that the gas molecules or the gas particles are negligible in size. Okay, so compared to the size of the container, we say that they are negligible in size, or they pretty much don't have a size. And we also assume that the gas is moving in complete random motion. Okay, there is nothing influencing the motion, it's completely at random. And these are the assumptions that you make for an ideal gas. And that then leads us to the ideal gas equation. And this is an equation that you need to know off by heart. And I'm just going to do it in this form over here and then explain what everything means. Okay, you should also be comfortable in rearranging this equation. So for example, if you're working out P, you should be comfortable in putting the V on that side by just doing everything divided by V. So I'm not going to cover how to rearrange equations in this video. That's something that you should be comfortable with. So explaining what each part of this equation means. And also the most important part of this is knowing what units everything should be in. Okay, so the P, the lowercase p that we use, this stands for the pressure of the gas. Okay, and the gas pressure must be in pascals, and pascals are given the symbol capital P lowercase a, so it must be in pascals. I'm going to cover in a few seconds how to convert between various units, but for now let's just cover that that should be in pascals. V, capital V in chemistry, stands for volume, and the volume here must be in meters cubed. Okay, just be careful because we have done everything so far in decimeters cubed or in centimeters cubed. Over here, for the ideal gas equation, it must be in meters cubed. Okay, right, the lowercase n just means the number of moles or the amount of substance. So I'm just going to put moles over here, and obviously units per moles are just moles. The R is something that you haven't come across before. Okay, R is what we call the gas constant, the capital R. So this is the gas constant. It's a constant, so that never changes, and it is found, so it's not something you need to memorize, it is found in the data sheet. So if you just open the data sheet, the gas constant R is written down here. Okay, so the gas constant is always going to be 8.314 joules per mole per Kelvin. Okay, but as I said, that's given to you in the data sheet. It's not something you should spend time memorizing. And last but not least, the T stands, or capital T in chemistry stands for temperature. And the temperature units that we must use are Kelvin. Okay, so you should come across Kelvin before, or the Kelvin temperature scale, and that's what we must use for our temperature in PV equals nRT. Okay, so I'm just going to go over some of the kind of common unit conversions that we need to know for these. So let's just kind of cover pressure first. So for pressure, we said that everything must be in pascals. Now, a lot of the time things are given to you in kilopascals. Okay, kilo just means 1,000, so 1,000 pascals in a kilopascal. So if we are therefore converting from a kilopascal to pascals, we just need to multiply by 1,000, like so. Okay, so for example, if you've got 1 kilopascal, to convert it into pascals, multiply by 1,000. So 1 kilopascal equals 1,000 pascals. Okay. Let's now have a look at volume conversions. So as we said, everything must be in meters cubed. A lot of the time things are in decimeters cubed. So to go from decimeters cubed to meters cubed, we must divide by 1,000. Okay. And sometimes if it's in centimeters cubed, to go to meters cubed, this one is going to be divided by 1,000,000. 1, 2, 3, like so. Okay. Let's move on to our next one, which is PV equals nRT. It's temperature. So we need to know how to convert to Kelvin. So if we've got something in degrees Celsius, which is what it will usually be in, to convert into Kelvin, we must add 273. Okay, so for example, if you've got 25 degrees Celsius, to convert it into Kelvin, we add 273, which is 298 Kelvin. Okay.